Hello everyone, welcome to the EasyPower Refresher webinar series. Today's topic is Transformer Protection Basics. Happy you all could join us. And as we are in the habit of doing, we'd like to start the session with a couple poll questions and very much would appreciate your response. So the first poll question, how long since coordination was checked or updated at facilities that you're familiar with? If you would respond, no obligation or liability, strictly just getting some feedback from the audience. And you might suspect that coordination is the topic today. It turns out it's not, but it does intersect with the discussions of transformer protection. So it looks like we're close to a quorum. Let's leave this open another 10 seconds. Here's how folks have weighed in. Excellent. And then the second question, has your facility experienced transformer or other equipment failures due to improper coordination? Again, this is more to the point of the cost of repair. Coordination is primarily to improve the reliability of the facility by allowing the downstream protective devices to trip or react if a remote fault is detected. Part of that scheme is to increase the delay upstream of protective devices. In some cases, those are meant to protect more expensive elements, so you can end up in a quandary between coordination and protecting fairly expensive pieces of the system. All right, here's how folks have weighed in on this. Okay, fairly wide distribution of responses. Excellent, thank you. So we're talking primarily about electrical transformers, and their failure modes can include both internal faults and through faults, or what's regarded as through faults. So we're going to be talking about the types of faults, the protection options, get into a little bit of a discussion of the transformer damage curves and how to utilize them as far as making sure your transformer is being protected as much as possible, and then look at the alternatives. Much of what we're covering today is included in the Buff book, also known as IEEE Standard 242. And these are not regulations or requirements, they're more guidelines. And hopefully it's offered as suggestions on how to work with your particular system. So very often, the transformer can be one of the most expensive elements in the system. And since they are a major system cost, it's important to consider what replacement or delays you will find if that transformer fails. And any way you look at it, loss of service can be costly. Sometimes even an installed spare or speccing out a transformer that's has more capacity than required is warranted. But in any case, protection scheme is justified, and basically you should be looking at the best protection scheme you can afford and make sure you're keeping up with maintenance and monitoring of the transformer itself. Transformers are susceptible to overloads, internal faults, through faults. We'll be talking about the transformer damage curves, but frankly, they're only there to compare against through faults. If you have internal faults, you've already damaged your transformer, and so the damage curves are really of no value at that point. It's important to understand the level of damage is important, and while it's virtually impossible to prevent wear and tear, if you will, or damage, partial damage to a transformer, that level of damage can make a big difference on what the alternatives are. For instance, winding failure is easier to repair than core damage. The windings can be removed from the tank and repaired physically, rewired, as opposed to a core damage, which could be catastrophic or involving a fire. So proper protection can limit the damage, but not always prevent the damage. And again, the bottom line, and this will come up repeatedly, preventive maintenance is important in this whole discussion. And this includes things like oil samples, testing the chemistry, testing the turns ratio, maybe power factor tests, and oil temperature tracking. The overloads basically have an effect on the winding over temperature. And the bottom line is the hotter the temperature, the shorter the life, because there's a potential for degrading the insulation of the transformer windings themselves. Internal faults can include phase to ground, winding to winding, turn to turn, and loss of oil, in addition to the through faults that we'll be discussing in a bit. High temperatures shorten the life of winding insulation. And the best protection for long-term overloading is monitoring or based upon tracking that winding temperature. Now, oil temperature in the bath is relatively easy to measure, as well as dry transformer temperature. And so as we look at the nameplate, it specifies the maximum allowable winding temperature rise. For instance, a typical value is 65 degrees C. And this is based upon a presumption that the 24-hour average temperature range temperature is 30 degrees Celsius. And so the way this is utilized is the 65-degree rise on top of the 30-degree ambient gives us 95 degrees average temperature for the windings, and then allow a 10-degree band for the hot spot, and that determines that 105-degree limit is the hottest you want your hot spot ever to be. Now, it won't immediately fail even if we exceed this temperature, but it will have an impact on the transformer life. Now, it is true that the lower the ambient temperature, the more capacity the transformer is capable of. And so frequently, people will have take advantage of that, take advantage of the fact that a lower ambient temperature allows more capacity for the transformer itself. And that's because the kVA rating is based on maintaining that winding temperature in a safe max mode based upon the specified average temperature. If the ambient temperature is higher, loading must be reduced, whereas if it's lower, you may be able to increase it. And so this gives us the ability, in fact, some cases, to have a seasonal rating that we can apply to the use of the loading on the transformer. Now, the best overload protection monitors are actually the winding temperatures. Now, that means that we need to have a a temperature sensing device, a thermocouple or an RTD in the vicinity of the hotspot. The next best location or ability to test the temperature is the oil temperature. And then transformer protection relays provide utilizing the thermal model of the transformer, and this can be based on loading, ambient, and measured temperatures in real time. Internal faults include short circuit and the windings themselves. These can be turn to turn and ground faults, but those can produce a very low magnitude fault current that may not be picked up by relays. And whereas we describe differential relays as the gold standard for detecting faults, they're really only viable in use for detecting major faults. So we're left, especially for faults that occur near to the neutral or in a low magnitude range, with the inability to use the differential relay capabilities. So that gets to surge protection. Transformer windings are the weak link. This is because surges, or the cause of surges, like lightning or switching transients, can produce spikes that could impact winding to winding voltage differential. So properly sized and installed surge arresters can reduce the winding failures. And you want to make sure, and these can be on both the primary and the secondary control connections on the transformer itself. And you want to make sure you locate the surge arresters as close to transformers as possible. And we'll talk a little bit more about transformer differential protection in a bit. But the way the relay works is that the current in, the sum total of the current in, equals the sum total of the current out. And if it doesn't, then that current's going someplace and it's probably a bad route. As I just mentioned, this won't be sensitive to very low magnitude faults, but it does require, as far as comparing the protection scheme to alternatives, which are primarily primary fusing, it is required that we have a breaker for the relay to trip upstream. And so the combination of the breaker and the relay can be fairly significant, but at the higher capacity transformers, it can be a modest investment compared to the cost of losing the transformer itself. At the same time, you need high quality CTs that won't saturate for external faults. And the biggest advantage is that they are very fast. The relays themselves are very fast acting. And the placement of the CTs describe the zone of protection. And in this case, we're including both the main breaker downstream and the transformer primary breaker upstream as part of that zone. And as we discussed in other webinars or discussions about coordination, this zone can be extended by placing the CTs lower in the distribution system, and that can determine better coverage on the higher current elements. So differential protection is considered the gold standard, but you need CTs on all three phases, both in and out. And again, you need to have a relatively costly main voltage, medium voltage or high voltage breaker to be able to switch the input current. An alternative then for very low level currents, detecting low level failures, is measuring the pressure relay or the pressure of the oil itself. And so that element's called a sudden pressure relay that can detect the pressure wave that occurs when oil pressure in the tank is changed. It's more sensitive. The scheme is more sensitive than differential relays. It can detect turn-to-turn faults, and it can be have a very fast response. Unfortunately, or it can be prone to nuisance tripping, so calibration and proper installation and maintenance is critical. And for conservator type transformers, or those that have a intermediate oil source, there's a similar type of relay that responds to the input and output flow to that reservoir. It's called a Buchholz relay. So these can be very sensitive and aid in the detection, especially if you're tracking the pressure, the oil level and temperature in combination with the relay status. Again, my recommendation would be to make sure you have a copy of the Buff book. This is chapter 11 that focuses on relay transformers. But yes, I'd be happy to share a copy of the slides when we post the video. Now, through faults are the result of an external fault in the secondary of the transformer. And the issue here is the high current that's involved when we do see a fault in the low voltage system. For instance, with a 5% impedance transformer, the effect of fault current can be 20 times typical values. And when we're considering heating and magnetic forces, that's I squared effect, then that 20 times factor is multiplied by itself, which potentially be 400 times normal current, and the heating and magnetic effects would be that much greater. And the primary fault damage type is overheating of the windings due to this long duration current. Mechanical damage, on the other hand, is due to the magnetic forces, which are caused when spikes or high current dumps are placed on the transformer, and the windings themselves have a tendency to repel each other from the core or even from windings to windings. So in that case, mechanical damage is cumulative and can be added up as multiple faults have happened during the life of the transformer. Now, ANSI C57 has transformer damage curves that define the magnitude and duration of through faults and describe what the transformer should be able to withstand. And this is in C57.109 for liquid transformers and C57.12.59 for dry. And what it describes, and what you will see when we get to EasyPower, is what I describe as the key points or the milestones in the TCC plot. So, and we'll show this in EasyPower here in a couple minutes. If I describe the time current characteristic curves of a transformer, the tool will show me with the tick mark here at the top the full load current at the voltage we have specified as a reference. And based upon what I've selected in the dialog box for the transformer, it will display the 100% damage curve. So this is a result of the capacity and the voltage and impedance ratio, and so it's a fixed value. The 100% damage curve is therefore described by the, as I say, the standard C57. The upper limit, which is the longer time exposure, although it's lower current. Now, those of you that aren't familiar with the TCC plots, we have time on the vertical axis and current on the horizontal axis. So at the lower current values, we can see that the damage curve will impact our transformer health on longer exposures, whereas mechanical damage will be the result of high current spikes, even at very low value of time. So this is less than a second, and we can see potential exposure to damage if we plot, in this case, 30,000 amps for even 2 seconds as far as mechanical damage. And then there's this dot at the bottom of the plot that's described as inrush, and we will get into more description on this a little bit later in the slides. But the overall goal then is to make sure my fault current and my load current will remain to the left side of the 100% damage curve, and any protection that I have for the transformer will not respond to the inrush plot. So my typical or my best case protective device will have a curve that comes where plots somewhere to the left of the 100% damage curve and to the right of the inrush curve. Now this is only for primary protection, and on secondary protection we don't have to worry about the inrush. Jonathan asked the question, sorry. Jonathan says, is there any way to accommodate the cumulative damage on the transformer damage curve? You're reading my mail, Jonathan. Thank you for the question. It's my next slide. Now, as we describe, C57.109 defines what's called a frequent fault curve. And so it gives us 4 different categories of both single and 3-phase transformers, and then an adjustment that's referred to as frequent fault. And what this amounts to is the ability of the transformer to survive that number of faults in its lifetime that have exceeded the frequent fault limit but have not exceeded the 100% damage limit. So this is also included in EasyPower automatically, and it shows up as this plot down at the bottom. And so this jagged plot, which comes out to be less current, is regarded as a frequent fault curve. So the damage curve is again for through faults. And we have the ability to select frequent versus infrequent. So frequent fault is this jag down at the bottom. The infrequent is the extension of the 100% damage curve. So if I design my system or my protection scheme to avoid entering this area of the damage curve, I've got a more conservative protection scheme than if I disregard that and I just potentially allow the system to routinely be affected by faults, only with reference to the 100% damage curve. So let's see if I can show what this means. 0, 1. They call these Z curves because they look like kind of a Z excused or stretched out. And so again, this is handled in EasyPower as I dialog the transformer parameters. So this is the transformer for this bus 2, and we're showing under our TCC plots, we're plotting the 100% withstand curve, the unbalanced derating curve that we'll talk about in a little bit, and then the frequent fault curves. So I want to see what those look like. If we go to coordination, pick out a single transformer and plot the TCC curves, we see the result of the two plots. Now, disregarding the inrush for a minute, the dotted line, hopefully you can see it, the dotted line on the right is the 100% damage curve. And if I open the dialog box to the TCC plot and I take off the 100% damage curve, that line disappears. I'm going to put it back on and then take off the frequent fault curve. Now the second line that we're talking about is the unbalanced derating curve, and we'll talk about that shortly. So I'm going to take it off. We start with the 100% damage curve and then use the frequent fault curve to do our coordination. I want to compare all three of these just real briefly to show you what to expect. I've saved a TCC. I'm comparing the three plots for these three different transformers. Cat 1, as we noticed from our chart from C57, does not have a frequent fault category. So we designed the protection scheme against a 100% damage curve. For category 2, you'll see it shows a 75% of maximum value as a frequent fault curve. And for categories 3 and 4, which are the very large power transformers, we, to be conservative, we try to stay under the 60% frequent fault curve. So this is all handled by EasyPower automatically. All right. I was going to show the reference voltage. So right now, if we look at the plots, the scale, we're showing this as current times 100 at the 480 volt range. EasyPower selected that because that's the lowest voltage in our system, and usually that'll be the higher current. And consequently, we see in a category 1, the current range goes from, looks like 4,000 amps down to 300 amps-ish. Now, as I'm moving the cursor around, you can see at the bottom of the screen the coordinates of the cursor location. So if I place this on the upper end of the damage curve for the category 1, I see my range is 400 amps at 426 seconds, whereas it tops out at 3,600 amps at just over 2 seconds. If I want to know what this is in primary voltage, our primary voltage scale, I can right click on the bus above, set it as a reference. And now we're talking lower current. Here we're talking 136 amps at 2 seconds and 14 amps at 447 seconds. And then I can look at the full load current. The cursor is at 5.26 amps. So that's the reference point that's used to calculate the loading and the protection scheme between the full load current and the 100% damage curve. So the first slides I had as far as the damages, what we can see, if my fault current exceeds this upper edge, then I potentially have insulation damage if I let that condition run for an extended period of time. Whereas if I have spikes that exceed this limit for a short period of time, I can get mechanical damage in the transformer itself. And as we just described, those are hard to pick up. Those types of damages are hard to pick up with my current sensing relays and fuses. And so that's why other schemes as far as the protection have to be considered for transformers. Now this is interesting, and it's non-trivial, and it's also non-intuitive. But basically, there's a difference based upon the configuration of the transformers. Typically, in a delta Y configuration, the per unit seen by the primary protection, in other words, if we have phase protection, phase current protection on the primary, it doesn't see something necessarily proportional to the secondary side. So if I have fault current on the secondary side and I'm expecting the primary protection to deal with it, I have to be aware of this non-conventional consideration. And again, winding damage on through faults is a function of through current on any one winding. So we must adjust the damage curve to take into account this difference in per unit current seen between the primary and the secondary. If you look at the way a delta system is connected, there's no ground connection on the primary side. And on the Y side, very often the neutral connection can be considered a ground, or is grounded. The point that I'm trying to make is if we measure the current through the transformer on the phase downstream, on the secondary, we can measure 1 per unit current, but it corresponds to the phase on the upstream. But in the case of a secondary fault on the secondary side, that 1 per unit current is shared by 2 phases on the primary. So again, currents for single line to ground faults on the Y side, where we have our protection on the primary side. So no, it's not nonlinear characteristics of the iron. This is strictly the phase winding shift. So there's a 30-degree shift just automatically in the current versus voltage realm, but in the magnitude of the current for a line to ground fault downstream, we need to adjust the fact that on the primary side, we're only looking at 58% of what that current is. So the point is we need to have a more sensitive protective device if we're using primary protection. And that's taken into account by offsetting that damage curve when seen by a primary device or primary protection. Now again, this applies only for ground faults on the secondary, and it applies only for primary protection. And again, EasyPower does this automatically, and that's why I'm kind of hammering on this. Let me figure out which one I'm looking for. Ground current TCC. And it's important to understand this is only for primary protection. So let's kind of not save this. Okay, and so let's just look at this. If I plot this curve for this transformer, I see on the TCC plot 2 curves. And as I mentioned before, that second curve is the unbalanced derating curve. If I take it off, I'm left with a 100% damage curve. So the message is, if I have primary protection, in other words, if my protection is a fuse in the primary side, then I want to make sure it responds before it gets to this shifted curve. Now, let's see. Let me go back and compare these three, because it'll change based upon how I've configured my ground. Notice here I have high resistance ground, hard ground, and no ground. So let's see how I've done that. Let's look at the the hard ground first. That's just what we were seeing. And so if I have primary protection, I need to make sure it stays clear. It protects me from currents that potentially exceed this shifted curve. Now, if I have secondary protection, I can disregard that curve and make sure that I'm not exceeding the 100% damage curve or the frequent fault curve. If we look at the hard ground, we just did that. Let's look at high resistance ground, and this kind of gives you a clue or suggestion. It doesn't show that second curve, but it does show the current through the fuse. This is another point I didn't emphasize. When I'm plotting a faulted bus, the tool shows me a tick mark through any protective device that's sensing that current. So in this case, we have a fuse here in the primary. The fault on the secondary, because of the resistor, I have 100 amps limitation on the amount of ground current I can produce. But if I look at the current in the primary, that's only 2 amps, and that's way down here on my scale. And so there's no chance that that's going to trip a primary protection anytime. So that's just a fact. And I'll kind of reemphasize that here in a second. And then if we look at a no ground situation where we have a ungrounded delta to an ungrounded Y, again, there's no difference between ground current and I'm looking at a line to ground fault, and there's no ground current as a result of the system having no ground at that point. Okay. Again, EasyPower takes this into account and handles it pretty nicely. So the takeaways here is if I'm focused on primary protection, I need to take into account the situation on my grounding transformer, specifically for a line to ground fault. Now for a three-phase fault, it doesn't matter because now we have full current going through the fuse, and we need to make sure we stay clear of that 100% curve. Okay. Now, and so that gives us this 58% adjustment for a delta Y. There's also an 85% shift on a delta-delta, and again, this is handled automatically by EasyPower. Now, in the National Electrical Code, Table 450-3, it shows the max settings for transformer overcurrent protection as a percentage of full load current. So based upon the location, whether it's any location or supervised, we have systems primarily that are monitored and operated by qualified personnel. That's considered a supervised installation. And we have the ability to look at primary voltages over 1,000 volts and secondary voltages over and under 1,000. And then whether we're not using breaker on the primary, fuse on the primary, and breakers, fuses on the secondary. And what we see is the potential for going to 600% of the full load current, 6 times the full load current with a breaker in the primary. That doesn't mean we have to go to 600% because we're cutting it pretty close as far as the damage curve. So let's look at my 300% fuse. This is where the rubber meets the road as far as what we choose to do for transformer protection. Let's get rid of this and go to the fuse. So according to the chart, if we have 1,000 volts, 1,000 kVA, and 13.8 volts on the primary and 480 volts, we could have 300% value of fuse for protection. And so if we go to coordination, let's plot the fuse and the transformer. Okay, so we're looking at a three-phase fault. The straight lines here on the right are the cable damage curves. And so again, we don't want our current time plot to exceed this rating for the cable. And yet, if we look at our fuse protection in the primary, this is rated at 50 amps, and our full load current in the 480 volt range is 725. So I'm going to reference this bus. I want to look down here at my coordinates and set this over the full load plot or tick mark. I see the full load current in the primary is 41 amps. So 300% times that would be 120 amps. And so the 50E looks like it's about 125E as far as full current. The point I want to make is you can see how inadequate the fuse is for protection because there's some area here that I don't have protection from my single line to ground. If we look at a single line to ground fault, I guess I can fall down here. So I'm seeing 276 amps in the primary, and in that current here at half cycle, and here at 30 cycles, this shows protection for my frequent fault potentially, but it doesn't have protection for this lower level long-term current. So that's one of the reasons that fuses are not that acceptable, or at least have some considerations that you need to make sure your circuit covers this part. Now again, the fuse is in the primary, and so it's doing a not quite adequate job at protecting the transformer from both the single line to ground faults and the frequent fault curves. Okay, not trying to cap on fuses, I'm just showing how to determine that effective coverage both for a three-phase fault and a single-phase fault. Now again, that we're not violating the the recommendation table, we're still staying under the 300%, but it's not adequate enough for the purposes of this particular design. Okay. Question says, using the table, is it possible that we oversize protection as a result to get high arc flash values? And that's another great point, is that another problem with fuses is that it's not going to be an adequate protection for arc flash. So if we look at the fault on this particular bus, because we have, I mean, this is not bad, but it's also not necessarily good protection. Yeah. So this is just a short cable. In fact, my paradox example, this is limiting to 16,000 amps, so that's pretty high, and it's potentially going to exceed the damage on the cable itself. So this table should not really be considered for arc flash protection. This is strictly the restrictions for transformer protection, and it may not be adequate to do coordination downstream. Okay, so much for that. Now just a real quick rehash of the inrush. When we're considering primary protection, whatever we have, whether it's a breaker or a fuse, we need to stay to the right of the inrush plot. So here we have roughly 8 to 10 times full load current for 1/10 of a second, and this will be based on the self-cooled rating. And we see that neither of these devices, presumably in the primary side, will be affected by the inrush. And most of the problem is that the inrush current is very much harmonic included for harmonic currents, and it's difficult to know their response on a protective device. Okay, we noticed the TCC plots, we can control what we're showing on the TCC plot itself, and you can take these off the plot, especially the derating curve, if you're not looking at single line to ground primary protection. So the question is how to improve transformer protection. Transformers, again, can be very expensive and catastrophic failures if we haven't designed a procedure to take care of potential damage. So for better protection, use breakers, not fuses, and breakers include relays and breaker combinations. For transformer protection against overcurrent, differential protection is the gold standard. And then for incipient faults, very small magnitude pressure detection and or tracking gas chemistry can be a more effective procedure. Now we described the delta Y impact on primary protection, but there's others, and there's other schemes that are used in the industry. These EasyPower takes care of automatically, but there's something to take into account based upon what your particular system is doing. Now, I haven't talked about resistance grounding other than that one example. The most common fault in the industry is a line to ground fault. And the issue is if it's not properly dealt with, it can be high enough current and potentially have an arc that can migrate to a full-blown three-phase fault. And so it behooves system designers to pay attention to the possibility of limiting the amount of current in a single line to ground fault. One of the ways to do that is with high resistance ground. And so, as I showed in that one example, resistance grounding can be accommodated in multiple ways. But again, to determine or remove the potential for grounding to be a problem, you should have all your sources in the same mode of limiting maximum ground current. To recap, it's difficult to provide full through fault protection with only primary fuses. Now, if you compare expulsion fuses with current limiting fuses, the current limiting fuse has more of a vertical slope to it. This gold band over here on the right is a current limiting fuse, and trying to use it in a primary protection mode, we can get frequent fault coverage, but we don't have coverage at the higher time delay at lower currents. Whereas expulsion fuse can be a little bit more accommodating as far as the slope, and this one's on the secondary side and can be worked in conjunction with the upstream breaker. A primary breaker is required for more advanced protection. It also helps with downstream arc protection. Multifunction transformer relays provide good transformer protection, but you really need a backup because you don't want to have all your eggs in one basket when it comes to protecting the transformer that has such high value. So here's a typical protection scheme that's offered. A multifunction relay that can include differential, ground, phase overcurrent, and then a backup relay, again, maybe lower capabilities, looking only at overcurrent, but the ability to cover multiple types of faults within the zone. And then there's, as far as comparing this against a fuse, it can be considerably more investment, but better coverage. More investment because the relay itself can be expensive. The CTs have to be selected, and then the medium voltage breaker has an investment. And just one more quick rehash on the inrush, because there was a question there. Transformer protection must ride through the inrush. In other words, if I have primary protection for my transformer, it can't be allowed to be sensitive. You don't want it to be sensitive to the inrush plot, which generally is at the 10th of the second range. Here's a good question from Jesus. Using the 450-3 chart, is it possible that we oversize protection as a result of the high arc flash values? So I believe what he's referring to is the ability to oversize or include additional capacity in the transformer so I can fall within the damage curves with my primary protection. And that's a good way to, in other words, the lower the draw on the transformer, the better we've extended the life. So temperature and time both affect the capacity utilization. And so the answer is, yeah, potentially that's one way to get there, but you do end up with higher current potential on a fault because of the extra capacity on the transformer. So it's a something you have to pay for at some point in the design, but overall the ability to extend the life of the transformer and reduce the service aspect can be substantial. Okay, I think that covers what I meant to cover today. We will include a copy of the slides when we post the video. Thank you everyone for joining us. Be sure to check out the new webinars we have scheduled, and we're doing live virtual training. Actually, this year we'll have a live in-person training in July. So check out the website to get updates on that. Thank you for joining us. We'll talk to you later.